What if I told you that anyone who sets foot on Mars is actually taking a one-way trip? I'm not talking about lack of fuel, limited budget, or insufficient technology. The problem is much deeper and more frightening than that. The real obstacle to returning lies within each astronaut. The human body itself becomes a biological prison. Today we're going to dive into one of the most disturbing secrets of space exploration, a topic that space agencies prefer not to highlight in their glamorous presentations. We'll explore why astronauts who reach the red planet may never be able to return home, and how this reality is secretly shaping space colonization plans. Since Galileo pointed his telescope at the night sky, humanity has dreamed of reaching other worlds. Mars, with its reddish coloration visible to the naked eye, has always occupied a special place in our collective imagination. Science fiction writers have sold us the idea of Martian cities, of colonists terraforming the planet, of a second home for humanity. But there's a disturbing detail that rarely appears in Hollywood movies or the optimistic presentations of space agencies. Our bodies simply weren't designed by evolution to survive outside Earth. And the more we learn about the effects of prolonged space travel, the darker this reality becomes. When NASA sent the first astronauts to the moon in the late 1960s, we were talking about missions that lasted only a few days. The journey to our natural satellite took approximately 72 hours, 3 days of travel in each direction. Astronauts spent at most a few hours on the lunar surface before returning. Total time away from Earth? Little more than a week. Now let's contrast this with a mission to Mars. We're talking about an expedition that takes between 6 and 9 months just to reach the destination. That's right, half a year or more confined in a space capsule the size of a small apartment. But the journey is just the beginning of the problem. Once on Mars, astronauts can't simply turn around and come home. Because of the orbital alignment between Earth and Mars, there's a window of opportunity for return that only opens approximately every 2 years. This means a typical Mars mission would require astronauts to remain on the red planet for about 18 to 20 months, waiting for the correct orbital geometry to begin the return journey. Add it all up, 6 to 9 months outbound, 18 to 20 months on Mars, plus 6 to 9 months back. We're talking about a total mission of 2.5 to 3 years. 2.5 to 3 years during which the human body will be subjected to conditions for which it absolutely did not evolve. And this is where the story becomes truly terrifying. Let's start with the most obvious problem, but perhaps the most underestimated: gravity, or rather, the lack of it. Throughout our evolution as a species, actually, throughout the evolution of complex life on Earth, our bodies developed under the constant influence of 9.8 meters per second squared of gravitational acceleration. Every cell, every bone, every muscle was shaped by this invisible force that pulls us down at every moment of our lives. Our skeleton is not a static, dead structure. It's living tissue that is constantly remodeling itself. Cells called osteoblasts build new bone tissue, while cells called osteoclasts reabsorb old bone. Under normal conditions on Earth, these processes are in balance, keeping our bones strong and healthy. But this balance crucially depends on mechanical stress. When you walk, run, or simply stand, you're constantly putting pressure on your skeleton. This pressure signals osteoblasts to continue building new bone. Remove this pressure, and the balance breaks dramatically. Mars's gravity is only 38% of Earth's. This means every step you take on Mars exerts less than half the force it would on Earth. And during the 6 to 9 month journey to get there, absolute zero gravity. Astronauts on the International Space Station lose between 1% and 2% of their bone mass per month in microgravity. Let that information sink in for a moment. In a single month in space, you lose as much bone tissue as a postmenopausal woman would lose in an entire year. And unlike osteoporosis, which tends to mainly affect the spine and hip, bone loss in space is systematic. It affects the entire skeleton. Now multiply that by 6 to 9 months of travel, plus 18 to 20 months in reduced Martian gravity. Even with the most rigorous exercise protocols, and astronauts on the ISS exercise 2 hours a day, every day, bone loss is inevitable and substantial. But here's the part that really scares space doctors. This bone loss may not be reversible. Studies with astronauts who returned from long missions on the ISS show that even after a year back on Earth, many don't fully recover the bone density they had before leaving, and we're talking about 6-month missions, not 3 years. Bones aren't the only gravitational problem. Our muscles also suffer dramatic atrophy. Without the constant resistance of Earth's gravity, muscles simply don't need to be strong anymore. They shrink, lose muscle fiber, become weak. Again, astronauts on the ISS combat this with intense daily exercise. But even so, muscle loss is significant. And we're not just talking about the muscles you can see, your biceps, quadriceps, abs. The deep postural muscles that keep your spine aligned, the small stabilizer muscles around each joint, even the smooth muscles in your blood vessels, all atrophy. And the most important muscle of all, your heart. The heart is, after all, just a muscle. A muscle that on Earth needs to pump blood against gravity to feed your brain and upper extremities. In reduced or zero gravity, this work becomes much easier. And just like any muscle that isn't challenged, the heart atrophies. Ultrasound studies on astronauts show that the heart literally shrinks in space, becoming more spherical and less efficient. Total blood volume in the body decreases by about 10% to 15% in the first weeks in space. The body simply decides it doesn't need so much fluid circulating. Now imagine returning to Earth after 3 years. Imagine trying to stand when your skeleton has lost 30% or more of its density. Imagine your atrophied heart trying to pump reduced blood against full Earth gravity. Imagine muscles that haven't supported real weight for years, trying to keep you upright. The results would be catastrophic. Bones so fragile they could fracture simply from the impact of standing up. A heart that can't pump enough blood to the brain, causing fainting and potentially stroke. Muscles unable to support the body's own weight. In short, an astronaut who spent 3 years in transit and on Mars would likely be unable to survive the return to Earth's gravity, even if they arrived alive on the surface. But gravity is only part of the story. The second major problem is something you can't see, feel, or smell, but that is silently destroying your body every second in space: cosmic radiation. Here on Earth, we live under an invisible but extraordinarily effective protection. Our planet's magnetic field, generated by the spinning molten iron core at the center of Earth, creates a protective bubble called the magnetosphere. This bubble extends thousands of kilometers into space and deflects most of the deadly radiation that the Sun and galaxy constantly hurl in our direction. Additionally, our atmosphere provides another layer of protection. Even radiation that manages to pass through the magnetosphere is largely absorbed by air molecules before reaching the surface. The result: here on Earth's surface, we receive about 0.3 to 0.6 centisemi of gray, centigrade, or CGY of radiation per year from natural sources. It's an insignificant amount, so small that our cellular DNA repair mechanisms can easily handle any damage caused. Now let's go to space. Once you leave the protection of Earth's magnetosphere, the story changes dramatically. In interplanetary space, astronauts would be exposed to approximately 20 to 30 CGY per year, about 50 to 100 times more radiation than on Earth. And on Mars. Although the planet offers some protection simply by being below you, the planet's mass blocks about half the radiation. Mars has no significant magnetic field, and its atmosphere is only 1% the density of Earth's atmosphere. Exposure on the Martian surface would be about 15 to 20 CGI per year. Do the math. 6 to 9 months of travel at 25 CG per year, plus 18 to 20 months on Mars at 17 CG per year, plus another 6 to 9 months back. An astronaut on a 3-year Mars mission would receive a cumulative dose of approximately 50 to 70 CG per year radiation. To put this in perspective, NASA currently limits astronauts to a lifetime dose that should not increase their risk of fatal cancer by more than 3%. For a 40-year-old man, that limit is about 100 CGY over an entire career. A single Mars mission would consume half to 2/3 of that lifetime limit. But cancer isn't the only concern, nor even necessarily the biggest one. Cosmic radiation consists largely of heavy atomic nuclei traveling at near light speeds, particles so energetic they can pass through a spacecraft, a spacesuit, and a human body as if they were made of paper. When these particles hit the brain, they leave trails of cellular destruction in their path. Studies on animals exposed to simulated cosmic radiation show concerning damage to cognitive function, including memory problems, learning difficulties, and behavioral changes. There's growing evidence that exposure to space radiation can accelerate the development of neurodegenerative diseases like Alzheimer's. The eyes are particularly vulnerable. Many astronauts who spent significant time in space develop early cataracts. Radiation can also damage blood vessels, increasing the risk of cardiovascular disease decades after return. And then there's the immune system. Cosmic radiation suppresses immune function, leaving astronauts more vulnerable to infections. Combined with stress, confinement, and other adverse mission conditions, this creates a perfect storm for health problems. Currently, we don't have a good solution to the radiation problem. Traditional metal shielding is too heavy to be practical, and yet still offers limited protection against the most energetic particles. Worse still, when cosmic radiation hits metal atoms, it can create showers of secondary radiation that are sometimes worse than the primary radiation. Some proposals involve using water or polyethylene as shielding, since light elements are better at absorbing cosmic radiation. But even then, you'd need meters of material thickness for adequate protection, something simply impractical with current propulsion technology. The result is that any astronaut who goes to Mars will return, if they return, with permanently damaged DNA, greater lifetime cancer risk, possible cognitive impairment, and a weakened immune system. This is a sentence that cannot be undone. Beyond bones, muscles, and radiation, there's a cascade of other physiological problems that make returning to Earth increasingly unlikely the longer an astronaut spends away. The cardiovascular system undergoes fundamental reorganization in space. On Earth, your heart and blood vessels constantly work against gravity. The veins in your legs have special valves to prevent blood from flowing back down. Blood vessels in the brain automatically constrict and dilate to maintain constant pressure, regardless of whether you're lying down, sitting, or standing. In microgravity, this entire finely tuned system becomes unnecessary. Body fluids redistribute, with more blood going to the chest and head. That's why astronauts in space often have puffy faces and stuffy noses. It's as if they're upside down all the time. The body responds by decreasing total blood volume and allowing blood vessels to become more compliant. The baroreceptors, blood pressure sensors in the neck and chest, recalibrate to the new environment. The heart pumps less vigorously because it doesn't need to work as hard. When an astronaut returns to Earth after months in space, this entire system needs to readapt quickly. But after years, readaptation may be impossible. The body may have changed so fundamentally that it simply can no longer regulate blood pressure adequately in Earth's gravity. This leads to a condition known as orthostatic intolerance, the inability to stand without fainting. Astronauts returning from 6-month missions on the ISS frequently experience this temporarily. After 3 years, it may be permanent or take years to resolve, if it resolves at all. There's also the problem of fluid loss. As mentioned, blood volume decreases significantly in space. But there's also plasma loss, the liquid component of blood. The total number of red blood cells decreases because the body detects it doesn't need as much oxygen transported when not exercising against gravity. Returning to Earth means this reduced blood needs to work much harder, but there's no way to recharge instantly. It takes weeks to months for the body to produce enough blood again. During this time, the astronaut would be extremely vulnerable. The vestibular system, your sense of balance and spatial orientation, also suffers profoundly. In the first days in space, most astronauts experience severe space sickness because the vestibular system, which evolved always assuming the presence of gravity, becomes completely confused. Eventually, it adapts, learning to ignore gravitational signals and rely more on vision. But this adaptation makes the return even more difficult. The brain needs to relearn how to interpret gravitational signals. After short missions, this takes a few days. After years? Nobody knows, but it may be that some astronauts never fully recover normal balance on Earth. There are even concerns about vision. Many astronauts develop a condition called VIP, visual impairment intracranial pressure, where fluid redistribution causes increased intracranial pressure, flattening the eyeball and causing vision changes. In some cases, these changes are permanent. The list continues: reduced lung function, metabolic changes, hormonal changes, chronic sleep problems due to lack of natural day-night cycles, and even changes in gene expression that can affect everything from immune function to the aging process. We can't forget the psychological dimension, which, while not physically preventing return, certainly complicates everything. 3 years confined in tiny spaces, with the same small group of people, without real privacy, without nature, without the possibility of simply going out for a walk when you need space, without the ability to have a real-time conversation with loved ones on Earth due to communication delays of up to 20 minutes in each direction when Mars is most distant. Studies of terrestrial analogs, like winter polar expeditions, Antarctic base missions, and isolation simulations, consistently show that prolonged isolation causes a variety of psychological problems: depression, anxiety, interpersonal conflicts, sleep problems, and occasionally even psychotic episodes. And that's in environments where you at least know you could be evacuated in an emergency, where you can feel the wind on your face or see the horizon. On Mars, there's no possible evacuation. If something goes wrong, if you freak out, if you develop a serious medical condition, there's no quick trip home. You're on your own for at least 2 years. The psychological impact of knowing you can't go back can be devastating. Even if technically possible, the perception of being permanently cut off from Earth, from all the places and people you've known, can be unbearable for many. So let's put all these puzzle pieces together and look at the complete picture. An astronaut who travels to Mars and spends almost 2 years there will have lost 30% or more of their bone mass, leaving their skeleton too fragile to support Earth's gravity without multiple fractures, experienced severe muscle atrophy, including in the heart, potentially making them unable to circulate blood adequately in Earth's gravity, accumulated the equivalent of decades of radiation exposure with permanently damaged DNA and drastically elevated cancer risk. Then suffered possible cognitive impairment due to cosmic radiation, developed potentially permanent orthostatic intolerance, making it impossible to simply stand on Earth without fainting, reduced blood volume and fundamentally reconfigured cardiovascular system, possible permanent vision damage, marginalizou no immune system, possibly deep psychological trauma. Now, here's the question nobody wants to ask out loud. How do you bring this person back to Earth safely? Even if you manage to build a ship with adequate radiation shielding for the return trip, which we still don't know how to do, even if you develop perfect exercise protocols to minimize bone and muscle loss, which don't yet exist, you're still bringing back someone whose body has become fundamentally adapted to an alien environment. The entry into Earth's atmosphere would impose multiple gravities of force, G-forces that an atrophied body simply may not withstand. The astronaut might not survive the landing. And even if they survive the landing, what then? Months or years of intense rehabilitation with uncertain chances of complete recovery. The reality is that much of the damage, especially radiation exposure and possibly part of the bone loss, is irreversible. This raises profound ethical questions. Do we have the right to send human beings on missions, knowing it's effectively a sentence of permanent exile? Or at best, that they'll return irreversibly damaged? Some people argue we should be honest about this from the start, that Mars missions should be framed as permanent colonization, not as exploration missions with planned return. If you go to Mars, you stay on Mars, you build a life there, in reduced gravity, under radiation protection domes. You become Martian, not Earthling. Others argue we need to develop the necessary technology, artificial gravity through ship rotation, effective radiation shielding, advanced medical countermeasures before sending anyone. That it would be morally irresponsible to proceed without these protections. The uncomfortable truth is that, with current technology, any crewed mission to Mars would be, in practice, a one-way mission. Not because we can't build rockets to bring people back, we can, but because the astronauts themselves, after years in space and on Mars, would have transformed into something that can no longer survive on Earth. They would be, in a way, the first true generation of post-terrestrial humans, not by choice or design, but by biological necessity. Their bodies would have crossed a threshold beyond which there is no safe return. Does this make Mars exploration impossible? Not necessarily, but it means we need to be brutally honest about what we're asking of astronauts. We're not asking them to make a dangerous trip with expected return. We're asking them to become permanent exiles, to leave behind everything and everyone they know, knowing they'll never again feel rain on their skin, never again dive in the ocean, never again embrace their loved ones on Earth. It's an almost incomprehensible sacrifice, and yet, when NASA and other space agencies eventually make the call for volunteers for Mars missions, I have no doubt that thousands will volunteer, because that's the power of the human spirit of exploration. Because some people look at the unknown, and, despite all the risks, despite the certainty of never returning, still say, "I'll go." The first Martians won't just be astronauts or scientists. They'll be pioneers in the truest and most tragic sense of the word, people who venture into the wilderness knowing there's no way back home. They'll be heroes, certainly, but they'll also be, in a way, martyrs. The question for us, as a society, is, when we have the technological capability to send humans to Mars, will we also have the wisdom and moral courage to do it the right way? Will we wait until we develop adequate radiation protection, artificial gravity, and effective medical countermeasures? Or will we proceed anyway, sacrificing those first brave explorers? And the question for you watching this now, knowing everything you've just learned about irreversible bone loss, radiation that permanently damages your DNA, the heart that atrophies, the practical impossibility of returning, would you still go? If you were given the chance to be one of the first humans to set foot on Mars, knowing it would be a sentence of permanent exile, would you accept? It's a question that may seem hypothetical now, but within a decade or two, it will be very real for a select group of individuals who will have to make that decision. Mars calls to us. The question is, how high is the price we're willing to pay to answer? If this video made you think, if it changed your perspective on space exploration, leave your like and share it with someone who should also know about this, and leave in the comments. Knowing all this, would you embark on a Mars mission? Or do you think we should wait until we have better technology? If you want to continue exploring the real and fascinating challenges of space exploration, not the Hollywood version, but the real science, subscribe to the channel and turn on notifications. We have much more content about the mysteries, dangers, and wonders of the cosmos. Until the next video, and remember, space may be the final frontier, but it's also the most hostile environment humanity has ever faced. Respect to anyone brave enough to cross that frontier, knowing they may never return.